Okay, let's talk. It's about communication capacity bounds from information causality. The figure is a top trade.
Thanks for the introduction. So let's start. I'll start with a very simple question. Say Alice writes a 5-page letter to Bob. What's the best that he can read out of it? At most 5 pages, maybe 3 if his handwriting is bad. That's the essence of information causality. So for such scenarios where you have a communication, one can roughly show the following, that in some way of measurement, the information what Bob has about Alice is bounded by the capacity of the medium between them. More specifically, we can say that something like this holds true, where Alice would have a bit string, say A0 to AN, and Bob's trying to read that bit string. The total information of Alice's data is bounded by the capacity of the communication. I'll start with a brief outline. I start with a small recap of what has been done here. Then we'll show how we extend this principle to a wider class of scenarios. In the end, we'll see its implications on communication complexity. We start with a quick recap. So what's been done? Turns out quite a lot. So this is just the description of the scenario. I have two parties separated, share a source. Alice has her access to a bit string, say 0 to AN. Bob gets a number which is a label, and Bob's goal is to guess the corresponding bit string. We recently devised an algorithm which would take the information causality statement and turns it into a polynomial Bell inequality. This thing is nice because the mutual information is a complicated expression of logarithms and entropies, and it's very hard to extract the constraints. And so our algorithm is protocol agnostic and works for any input and output setting, and it gives us super simple polynomial equality. What can we do with that? We can bound the quantum set. Many of you might have seen such a picture. It's just a representation of the space of correlations where each point represents a probability distribution. The inner box represents local probabilities, the green circle is the quantum set, and the blue circle is the set of all distributions satisfying causality or non-signaling. And in some cases, these inequalities can also recover the quantum boundary. One thing to note here is that this principle does not assume any formalism, any Hilbert phase structure, state space operator, and so on. It is completely empirical. Using these, we can also prove some cute stuff like random access coding bounds for 2n1 scenarios and even higher. Now what we do is we extend it to a higher class of scenarios, something like this. Say you have a referee, and referee gives Alice and Bob some inputs, and they are supposed to and they want to compute a distributed function. Both of them output 1 bit, whose sum would be the final guess of the function. For such a scenario, we can show that something like that holds true. We can warm up with that. We choose a very simple function, just the index function. The goal here is Alice has a bit string again, Bob has an index, Bob has to guess Alice's yth bit. So now notice this set here. In this statement, we have a precondition on the image values of the function, which for this case would just be the bit string set. If we plug it back, we get something like this, which you may recognize is just the original IC statement. Make sense? Now, if there's anything which you will take from this slide, it's this one. Consider the inner product function. We do something similar. We write out all the pre-image set for the inner product. We'll get these 4 values. These are the sums of the information causality statement. I replace these values with them, and now I get something like this. Now we notice each term in a no. The first one is just a constant term, so it vanishes. Second term is fine. The next one's also fine. And now here, I see that I have a conditioning on each of the bit strings. This thing is effectively deterministic. The settings on Bob's side, so to speak. So this term also dies. And effectively, we are left with that. And after a little bit of relabeling, you can see that this is nothing but the index function. So this is a curious fact. The index function is a fundamentally different function from the inner product function. And somehow under the lens of information causality, they are the same. Turns out this fact is true for any bit string, and a similar reduction also holds for the set disjointness function. Sense? Yep. Now, finally, what is the implications in communication complexity? We start with a brief review of what is it. Essentially, in any communication scenario, if we say that the complexity is non-trivial, we demand that there are functions which are hard to compute, in the sense that the amount of communication I need to do increases with the input size. Some functions are trivial, like parity, I just need to send one bit, or one-sided functions, they can be decided in a single bit. Some functions are slightly harder, like the inner product, equality, index. They cannot be decided in a single bit, and we would expect that the amount of communication that I need to do should increase with the message size. We can also have a randomized version where we ask for a given protocol, the winning probability should be strictly greater than 1/2 for all input sizes. Now we look at the slice again we had from before. There's this thing called PR boxes which collapse communication complexity. For those of you who don't know, this box has been the bane of information scientists for about 3 decades. These are these green guy on top. Van Dam in 99 showed that with enough PR boxes, any function can be decided in 1 bit, regardless of the input size. To give an example, suppose I have to compute the inner product for a 10 million bit string on Alice and Bob's side. Somehow, without any communication, or with just a single bit of communication, they can decide that function. Sound highly improbable. This thing was extended later to the case of noisy boxes. So it's just a PR box added with some count of noise. They showed that if the boxes win the CHHS game with a little bit probability, like say 90% or so, they also collapse communication complexity. That's this purple region on the top. Now, our goal is to see that our principle implies non-trivial communication complexity. So this is an intuitive proof of how that would go. Start with the statement, we split it out into terms. Now, if I demand that I'm winning a game, that means each of my winning probability should be greater than half. I would have this, and so forth. And since the winning probability is greater than half, my guess for each bit should be close. Say each of the guess should be closer to AI, so this mutual information should be roughly equal to 1. I would have that. So what does that tell us? If I want this thing to hold, that means that the capacity must be growing. Make sense? I can also frame this more rigorously. I would define some average winning probability, write down my statement, and use something called a Fano inequality. It's just a way to bound the mutual information in terms of entropies. I do some concavity argument and end up with this. Now, if I demand in this equation that I'm winning at greater than even odds, then my entropy is non-zero, and thus the message size m should scale with n. And that essentially means that this thing has a non-trivial communication complexity. Thus, any box which satisfies IC has to satisfy non-trivial communication complexity. Simple as that. But there's more. I take a look at it. What does this mean for me? That for a given constant p, the message size is omega n. It just means that the communication complexity of the index function is omega n. Fine. But we also remember a reduction from before, that the causality statements for index, for IP, and for disjointness are the same. This effectively means that their communication complexities must also be the same. Again, I have to stress, the statement was unaware of the structure of these functions. It was imposed that they are equal, and getting a bound for one of them gives me bounds for free. And thus, also, again, to stress again, these were theory independent. There was no mention of any Hilbert space or any complicated protocols or optimizing over some method or so forth. Now, having said that, it seems like the statement implies an equivalent structure on the space of functions, and thus we can in some sense classify it. That's exactly what we do. We consider the space of all functions of input length 2, and we get the following 8 classes. What these are doesn't matter so much as much the relative bounding power between them. We rank them in some sort of hierarchy and obtain something like that. Now these dotted lines are the reason why this is not on archive and I am sleep deprived. But for the fact, of the bold lines, this is how we would read it. You start at some point, and if you are up in the hierarchy, the lower classes are implied by the higher one, and within a hierarchy, every function would have the same communication complexity. So for example, consider class 4 from before. This is just the index class or the IP or the disjoint class, same thing. We can take it and then again plot some regions in the correlation space. And in this case, we exactly recover the quantum set. Nice. And also as a fun fact, we were able to prove that the disjointness function is the most non-local function in the entire space, generally requiring an exponential number of PR boxes to decide. In comparison, the inner product function only requires linearly many PR boxes to decide. Now I'll summarize. So we have an algorithm to derive quantum Bell inequalities, which is protocol agnostic and works for any scenario, any number of measurements, and so forth. We were able to extend the original principle from just the QRAC guessing game to any distributed scenario. And we saw that the reduction scheme implies an equivalent space structure on the space of functions. We also showed that our principle implies non-trivial communication complexity, and through that we can derive complexity bounds in a theory-independent manner. And at the end, we had a hierarchy of the functions for our classification. Now, the hierarchy imposes several questions. The most obvious one being, what about higher spaces? We see one such class exists where index, IP, and disjointness are the same. We also discovered another non-equivalent class which was given by the equality functions. In the space of binary string lengths, these were the only relevant two which we found. These were the top rectangle, so to speak. But we would expect that in higher dimension, there should be more different non-equivalent classes and so forth. Thanks.
Yeah, thank you for the talk. It seems that the principle works in the bipartite case. Do you know an extension to the multipartite scenario?
For information causality, there's not inherently multipartite extension. You could apply it to like bipartitions at a time, but this won't exactly be tight.
Okay, thank you.
Thank you for the talk. I have, I don't know, two basic questions. So one is, what is a PR box?
PR box, so you know non-signaling?
Sorry, non-signaling. Mm-hmm.
Yeah, so the non-signaling, the space of non-signaling functions is a polytope. And since it's a polytope, it should be able to describe by its extremal points. It's just one of these extremal points.
Okay. And you said it's not on archive now. Do you have a write-up somewhere?
Yes, in preparation. It was cited somewhere. You see that? Never mind.
Okay, so it's not up somewhere yet.
Yeah, I mean, it's here, but not up somewhere.
Thanks for the talk. It was nice result. So do you think you can use it to obtain sharper bounds for X or QRACs?
So the bounds which we had were already the quantum ones, so I don't think they can get sharper.
I see.
But for EARAC, these are not tight, and the fact that they are not tight is a Pandora's box, so to speak, because we don't know if the information causality set coincides with the quantum set.
Okay. Because you recover an X bound for index function.
Sorry,
You
again?
recover an X bound for index function, which is just a QRAC, right?
Yes.
I just wondering, okay, if you consider like more complicated versions of QRACs, you could obtain sharper bounds.
It's something which we did not try that much, but we were just tried this too, like in the QRAC notation, NP2 bounds, and this was exactly the quantum one.
But okay, for general one.
For general one, not really, because the thing, one problem with this is you don't know what's the best protocol.
Right.
Because the statement is, I mean, for better or worse, unaware of what the structure of the theory is.
I see. Fair enough. I see. Okay, thank you.
Thank you for the nice talk. Okay, my question is about something about the foundation of quantum theory. So some researchers want to try to found or characterize the mathematical model of quantum theory via information causality. And also sometimes some people can have idea about to derive some mathematical model of quantum theory through the communication complexity. Your result can your result state that for such a foundational scenario, information causality is stronger than any other
Yeah, for the
contributions?
principle of communication. Yes. So
So maybe so then you can say that. So can you say that? So if we can derive we can derive quantum theory through communication complexity, then you can
so
derive
if
the
I go back through my keyboard, almost there. Yeah. So it's impossible. This green circle is the quantum set. It's impossible for NTCC to derive quantum mechanics so far, or at least it's as hard as I see. Yeah, the king is dead.
Hi, thanks for the really nice results. Actually, I just wanted to clarify a point because the part where you try to relate the IC to the IC lower bound on the capacity to the communication complexity, because it's just the lower bound, right? But how can you get the statement that all the communication complexities are the same from the lower bound?
Because their information causality statements coincided.
Yeah, but that just gives you a lower bound on the capacity, isn't that right?
Well, the upper bound is also n, right? Because if I have the entire string, I can just send the entire string.
Right. Okay. Because the lower bound is n, so the upper.
And the upper.
Okay. I see. Okay, interesting. Thanks.
Okay.